10 minutes over today because we're going to need the time. All right. Hello, everyone, and welcome to Handmade Hero, the show where we code a complete game from scratch, live on Twitch. No libraries, no engines. This is essentially a series about how to program everything in games. So we cover everything, including how you would program an engine if you were making your own. And today we're doing a topic that is one of those topics that is straight to that point, because it's not something that you might do that much of if you're just doing very sort of fluffy, high-level game code, and that is optimization. Basically, we've gotten to a point where we finally have some code in Handmade Hero that we're calling that does enough work where it's actually causing us a frame rate problem. And so what we want to do is learn some optimization techniques to go ahead and speed that up so that it will not cause us a problem during development, right? And so our goal right now is not necessarily to optimize it down to like its fastest possible form or anything, but we do need to know enough optimization right now to be able to optimize that piece. And basically the principles of optimization are more or less always the same, whether or not you are trying to do the most optimal version of something or just an optimal enough version of something, because really they're the same process. It's just a question of when you stop iterating on that process. And so really it's a good time to introduce optimization and talk about how we do it, because we're going to do it at multiple points on the stream, and this is definitely one of those points. So I'm going to go over to the Blackboard and give a really quick introduction to optimization, how to think about it, and how we are going to be thinking about it. And then we're going to sort of start building a few primitives that we're going to need to do our optimization work. We will probably not do any actual optimization today, because as I'm about to talk about on the Blackboard, the first step to optimization never has anything to do with actually optimizing code. It has to do with measuring and determining a bunch of things about your code before you start. And if you don't do that, you're kind of missing out on a big part of optimization. So let's talk about that really quickly here on day 112. All right. So let's talk about optimization. What it is, how you do it, everything about optimization. First of all, I'd like to start with a caveat, which is I am not one of the world's best optimizers. You are not going to be getting any incredible gems of wisdom from me here. I am a good enough optimizer. I optimize code enough to get it to the place where it needs to be for shipping purposes, but I am not one of those people who you go to when it's like, oh my God, we have this thing and it needs to be optimized within an inch of its life. That is the other guys at Rad. You're talking about Jeff and Fabian there, or people who spend all their time working on optimization stuff. I'm not one of those guys. So what I'm giving is basically the generalist view of optimization, which is how do you make code so that it's fairly good and fairly performant. And typically a lot of the techniques apply, but there's a certain level beyond which I won't be able to guide you, which gets into things like crazy stuff like cache line aliasing issues and all these sorts of things. We won't really be getting into those other than to mention the fact that they exist. And if you want to be one of those guys who just spends all your time on optimization things, because there are people who really like that, that's like what they like to do, I'll sort of mention them as we go so that you're aware of what you need to go and learn in order to really push optimization like past sort of that the crazy point, if you will. All right. So essentially what optimization is understanding, okay, there is a CPU, right, and a GPU in your computer, okay? And everything that happens, every frame of your game, is going through one of these two things and oftentimes both, okay? They are both things which look incredibly similar. Both of these things are chips that are, either soldered onto your motherboard or on the motherboard and on a card and so on. They are chips. And what those chips do is they decode an instruction stream, right? So there's a bunch of instructions, and we've gone over this before, right? We looked at this in the very first streams. Basically, there's an encoding that basically tells them what to do. So they go over some instructions that are basically bytes that are in their native format. And for each one of those things, they do some computation, right? They do something. And typically, for the instructions that we tend to care about the most, are kind of fall into two broad categories, right? They're things that are like loads and stores, which are basically things that modify memory, right? So there's some memory somewhere, and they're going to do these loads and stores, which are basically grabbing stuff from memory and pulling it into the local registers or the cache of these things, operating on them. Or there's stores which are saying we've got computed stuff and we push it out, right? So there's those types of instructions which you tend to think about, and then there's ALU style instructions, right? And I guess we won't call it ALU, it's a little ambiguous. We'll just say there's basically math operations, right? There's stuff we want to do, right? And typically the way that those work nowadays, and this is a very, very important thing to understand regardless of which of these we're talking about, because I'm saying both of these things work this way now. Math tends to be wide, okay? It tends to be in something called SIMD, which is single instruction, multiple data, and it means exactly what it sounds like. There is one instruction, but it operates on multiple pieces of data at once. And typically, in the minimal case, this is 4 things, right? This is 0, 1, 2, 3 things, and they're all going to have the same thing happen to them. So you know the way that we've been looking at code, where we have stuff like float x equals, y plus 3. We have something like this. This is not at all how modern processors ever work pretty much at all, right? This does not happen in a CPU or a GPU ever, right? We write that only because we are not caring about whether the code is optimal or not. What will actually happen 99% of the time these days, if you write this piece of code, is that the processor will actually do this operation on 4 floating point values, right? So it'll actually do 4 x's plus 4 y's plus 3 replicated 4 times, and it will simply throw away 3 of the results and keep only 1 of them. I'm not joking, this is really true. That's what happens. And the reason for that is that most processors are designed in this way: single instruction, multiple data, and 4 is the minimum number that you would be throwing away. Actually, there's typically as many, as many as 8 in an Intel CPU, soon to go to 16, and in a GPU it could be as many as 64. Okay. Again, I wish I was making this up. I'm not making this up. So what that means is when you encounter a particular instruction, like I want to add 2 numbers together, or I want to multiply 2 numbers together, any math operation, you are typically talking about something that is either slightly wide, is at least 4 things wide, or absurdly wide, like 64 wide, 32 wide, that sort of thing. Okay. Why do they do that? What's the point of that, right? I mean, it sounds kind of crazy, right? The reason is because, and again, I'm not a hardware guy, so, this is sort of the hand-wavy reason. And if you want, a more detailed reason, you'd got to ask a serious hardware person, someone who works on chip design for a living. But basically, the hand-wavy reason is because it's not free for CPUs and GPUs to decode and process these instruction streams, right? There's a lot of work that goes on in these instruction streams. And let's think about what one of these instructions actually is, right? An instruction might be something like, say, add, right? And again, there's registers. We talked about these before. They're the things that processors operate on. And so you might say, like, add, the contents of R0. Well, actually, I guess we'll say we'll put something in R0. So add the contents of R1 and R2 and put it in R0, right? So we want to do like R1 plus R2, and we want to put that in R0, right? So that computes R0 equals R1 plus R2, right? This might be what's encoded in the actual processor, some bytes that encode the fact that we want to, add these things. And these registers, right, are just, some set, the working set, the smallest working set of things that the processor works on, right? Maybe there's 16 of them. Who knows how many there are, differs from processor to processor. But basically everything looks like this. And if you remember back to the beginning of Handmade Hero, you remember how it looked. Our instruction streams typically looked like grab something from memory, put it into one of these registers, grab another thing from memory, put it into one of these registers, operate on them, and then write the result back out from the destination register to memory, right? So to give a complete instruction stream just for people who don't remember that stuff very well, maybe we'd say, like, we want to load something into R1, so we load some memory into some register into R1. We load something into R2. We execute the add, which loads R1 and R2 together, right? And then we might store, right, that R0 out somewhere, right? So we load in 2 values into the registers of this processor. We add them together, and then we write them out, okay? So again, a really simple, stupid instruction stream, but I'm just getting you back in that feeling. We haven't talked about this in a while, so I'm just recalling back to the beginning of things, right? I want you to think back about that. That's what's actually happening inside the processor is stuff like this, okay? Now, what I'm trying to get into, what I'm trying to point out here for the purposes of the SIMD discussion is that this is not free. This is a bunch of circuits that actually have to do all this work. They have to select registers for add operations. They have to know that we're taking this and adding it to this and writing it into this. It has to look to see whether or not this gets used somewhere. Can it be multi-pipeline? Can we issue another add if there was another add after this that looked like this? Right? Could I issue these two in parallel or not? Well, the answer is no, because this one needs the result of that one, right? But if this was R4, it could, and blah, 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 right? So it's actually incredibly expensive, the work that it has to do to decode the instruction stream that's coming in, decide how to issue it, go find free units, because typically processors have multiple adding circuits in them, right? Figure out which adding circuits are free at any given time to do this add. Maybe this one goes to one and this one goes to a different one, blah, 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 right? So you can see that there's just a ton of stuff that goes in here. We won't go into hardly any of how that works because it's not super relevant unless you want to, again, go down the super crazy path of optimization where you need to start knowing about like arithmetic unit pairing and which reservation slots and whether this thing can issue on this cycle or the next cycle. There's all these sorts of things that you might want to get into, and you might want to know the full details here. That's true if you want to be a super hardcore optimizer. You do need to know that. We maybe won't ever really get into that on this stream because we probably won't need to, but the point is, it's incredibly, incredibly complicated. And that complexity means that if you can leverage, if you're going to typically do operations on a bunch of data at once, right? Then if it can leverage all of that thinking that it does here, right? To go ahead and make sure that when it figures out what it needs to do, it can do it on a lot of things at once. That's a total win in terms of circuitry there. And it means that the amount of actual memory that has to be spun through in order to decode the instructions is much less too, because if I have to say, if I'm going to load here and I can load 4 pieces of data at once, that's 4 less instructions, well, 3 less instructions, a quarter of the instructions to load the data, as if I had to do 4 instructions to load 4 things, right? Same with the adds. It's 3 less adds. I do 1 add and add 4 things instead of having to do 4 adds, right? So if you know that your heavy workloads can typically be written in this style, it saves a lot of complexity in the processor, and it saves a lot of instruction space, just the footprint, right? A lot less memory bandwidth that's just going into the processor in terms of, like, they call this an I cache typically. It's an instruction cache. It's the place where when you read out instruction streams and figure out what to do with them in terms of like what they actually mean for the microprocessor, basically that a lot more fits in there at that point, right? Because you just have less instructions. So basically all processors work this way now. SIMD is everywhere. There isn't a processor you're likely to program on at all, whether it's a CPU or a GPU, that ever doesn't look like this. And so what you need to think about, obviously, when you're in here, is when we are talking about optimization, the model that we're thinking about is this model. And we essentially have 3 parts to it, we might say, which I'll kind of codify now that I've got the SIMD out of the way. Hopefully you all understand what that means when I say that the instructions are wide. It means that they're operating on many things at once, right? So we have a few things to think about, right? We essentially have the instructions themselves. This is what the CPU or GPU has to actually do, okay? We've got the cache. We've got memory, right? And what we need to think about is we need to think about, all right, whenever we're talking about optimizing something, essentially everything that we're going to do, whether it's a CPU or GPU, again, always fits this model because this is all computers can do. It's always a question of moving things from memory into a cache, from a cache into some instruction set, basically. I mean, you're not really moving them. I guess you could say there's the registers, right? I'm trying to think of how to draw that, but if I have that, say, that add here, or I guess I'll do a load R0 something. We have to move things from memory, which is where the computer stores them, GPU or CPU, they both have memory. They're going to go into some kind of a local cache. They're going to get loaded into registers inside the processor, right? They're going to be manipulated like those ads we were talking about before. And then they're going to be written back, right? They're going to be written back to the cache, maybe in a different place, and then eventually back out to memory, okay? And whenever this is happening, these instructions are going to be wide. So basically, almost everything that we do is going to be one of those single instruction multiple data things, so it's going to be at least 4 things wide, possibly more, right? So the model for everything we do is we know we have an instruction stream. That instruction stream grabs things from memory and pulls them into the cache. It pulls them from the cache into the registers. It operates on the registers, figuring out something, computing some values, and then pushing stuff back out into the cache, which then goes back out to the memory, right? Okay, so we talked about this a little before. I'll just mention it briefly again. A cache is basically something that is on the processor usually. Sometimes it's not, but usually on the cache. And they have names like L1, L2, L3, and the number indicates how, essentially how removed they are from the CPU in a sense. You could think of the registers themselves, the thing that the CPU actually operates on, as an L0 in some sense, right? It's the things that the CPU actually directly addresses, and it is instantaneous for them to get them, essentially, right? It's not entirely true, but it's like the fastest thing for the processor to work on is its registers. Then it has series of diminishingly small memory, it has series of increasingly large memories it can access. The L1 cache, the L2 cache, the L3 cache sometimes might not have one, and then main memory, right? And the cost of getting things from each of these gets increasingly expensive as you go off. So whereas an L1 cache may be something like 16 cycles to grab from, and an L2 cache might be more than that, and an L3 cache more than that, up to main memory, which may be something like 300 cycles, right? And one of these instructions, like an add, might be 2 cycles, right? So if you figure like, okay, looking at how this works, if I want to talk about how expensive something is, I could think about the fact that as I sort of get further away from the instruction stream, those registers that I'm actually operating on, as I get further away from those, I get more and more expensive to basically how long it takes me to pull something in, right? Okay, so let's talk about this model for a little bit here, because there's a lot of stuff to cover. But just keep this in your mind. Basically, this diagram here, we're going to refer to it a lot. All right. So first, let's talk about these things I just said, which are cycles, right? Cycles are basically the smallest thing that the CPU enumerates work in, okay? So basically, when you ask the CPU to do something, typically it's going to take some of these, right? It takes some of these to do something, right? And what they more or less coincide with is processors themselves run at a certain rate, and they have internal clocking. It's far beyond my knowledge of how that clocking works. I'm sure it works very differently now from the old days when I sort of learned basically what it was. But this is sort of what the processor is doing. Every step, every cycle, it can do something, right? Each individual cycle, it can do something. So when we talk about a processor and we talk about how fast it is, like for example, this processor in this machine right here, excuse me, we can actually look at the details, or I thought we could look at the details. That's not what I want. Where is how do I get just the details of this computer? You know what I'm saying? Desktop, computer, there it is. So you can see this is a 3.19 gigahertz processor. It's actually got 2 of them in there. 3.2 gigahertz is the rated speed, so we'll use that for now. All right. So a 3.2 gigahertz processor, which is what it's in this machine, okay? Gigahertz is an SI unit, so it's actually 1,000. It's not 1024 like gigabytes, right? So a gigahertz is actually 1,000 times 1,000 times 1,000, right? 1,000, this would be kilohertz, this would be megahertz, this would be gigahertz, right? So we're talking about 3.2 times 1,000 times 1,000 times 1,000, right? That is how many cycles per second. Okay? That is how many cycles per second we expect this processor to run at, right? Now it could change, that can change sometimes because processors have lower power states, they have power saving cycles and stuff like that, they might underclock themselves, there's all kinds of reasons that it might fluctuate, but at maximum, when it is running full bore, that is what it will do. Right? So that means we have 3, 2, 0, excuse me, 0, 0, 0, 0, 0, 0, 0, 0, right? Basically 3.2 billion cycles per second, right? So that is how many the processor is actually going to issue, how many cycles it's going to go through in 1 second. Now, what's interesting about that, right? I'm going to go ahead and, even though we don't need it at the very moment, I want to open up Emacs so I can use the little quick calc feature we were using, right? Right, so if I do 3.2 times 1,000 times 1,000 times 1,000, right? There's my cycles. Oh, you know what? Can I don't know how to use the last, there it is. I love Emacs when it does that for you. Okay, so there's that. Now, we know that that's how many cycles per second, but we know we do 30 frames per second, right? Our game runs 30 frames a second, which means every frame, we have that many, right? That's how many of, oops, didn't mean for that to go away. Come back. That's how many we actually have, right? So you can see here we've got like 106 million, or like 107 million cycles per frame, right? So let's just write that down. 107 million cycles per frame. Okay? This is on the CPU. So what that means is we have 107 million cycles to get everything that we need to get done in a frame done, right? And if we don't get everything that we need to have done in a frame done in that 107 million cycles, our game will not hit 30 frames a second, right? It's that simple. And so the first essentially thing that I want you to think about in terms of optimization is you should always know what this number is, right? You should always start out by going, okay, given whatever it is I have to work with, right? What is actually the base amount of performance I even have to work with? What am I working with? What are those numbers, right? And this is the first primary number we need to think about. 107 million cycles per frame. That's how many cycles we have on one of the CPUs to do our work, right? Now, this is, of course, not entirely, that's not the entirety of the picture, because this is essentially one core on one CPU, right? Now, in a machine, there may be multiple processors, there may be multiple CPU cores, that sort of thing. And technically, each core actually gets this many, right? So really, depending on the machine we're targeting, let's say we have a 4-core machine or something like that, then we know we actually have more than this if we can divide up the work among multiple processors. But we're going to get to that in a second. For now, I just want you to focus on one core, on one CPU, we have this many cycles per frame. All of our work that has to be done on the CPU must fit into that number. Okay. Now, it's already a pretty low number, 107 million, right? It's not that high. And why do I say that? Well, think about how many pixels on the screen there would be at 1920 by 1080, right? Let's see, there's 2 million, right? So there's 2 million pixels on the screen at 1980 by 1020, right? An HD display, right? 2 million. So if you think about how many cycles per pixel there actually are to process, if we were doing, like software rendering like we're doing right now, there's not that many, right? There's like, something like 50 cycles a pixel, right? That's it, 50 cycles a pixel. Not a very large number, right? What's this number divided by 2, right? 107 divided by 2, like 50. Very, very small, right? It's not a very big number. So just want to sort of put that in your head that 107 million cycles per frame is actually not that many. This is why, you see a lot of stuff that doesn't run at 30 frames a second, right? You open up some kind of app and it's super laggy and weird and janky, and it's like, it's actually important that this number not be exceeded, and oftentimes things will, right? So anyway, that's the first thing I want you to think about, that many cycles per frame. Next thing, you won't ever actually get all 107 cycles per frame probably, right? Because, well, maybe sometimes you will, but other times there's stuff that needs to happen that's not your cycles, right? So for example, there's stuff that we call windows to display the frame, right? We have stuff we have to do. We call windows to get the state of the joystick and whatever, right? There's a bunch of stuff that we don't actually control that is using some of those cycles. So depending on which core and which CPU we're talking about, we may not even be talking about all 107 million cycles being for our use, right? But in today's world where there's multi-core, if you have a user whose machine has been set up to not have tons of like Adobe Acrobat running in the background and like, Acrobat Reader like sitting there checking for updates, Adobe Creative Cloud looking to see if its license is valid and everything else happening. Assuming that you have a user who's got a machine set up for gaming and it's relatively clean, maybe on a bunch of those cores you actually are getting 107 cycles per frame. But on at least one of them, which is the one where you interface with Windows, you don't. So that's the next thing to be aware of. All right. So let's keep that in mind. Just think about that, keep it in mind. The next thing, what is a cycle? What actually is it, right? Because we know that it's running at this rate, but we don't really know what that actually means, right? So it helps to have some understanding what actually happens in the CPU on something called a cycle, right? And so basically what will happen in a cycle, and again, this is a very, very high-level overview of what happens in a cycle in a processor. This is not a hardware explanation. It's just a mental model for you to understand roughly what is going on. So please take it with that large grain of salt. So what's happening in the cycle, first of all, right, is there is an assumption, presumably. Remember I told you there's that thing called an I-cache, right? So basically a processor usually has a thing that's some kind of a cache that has the instructions in it, and these things are actually decoded. They're usually in something called microcode, okay? And what microcode is they're not exactly necessarily the instructions that we see when we look at, when we start talking about optimizing things and looking at the instructions. They're not actually the ones that we see. They might be. So it might be that like an add, like something like this add, actually is just an add. Like it's just one instruction in the microcode. But there's other instructions that might be multiple microcode instructions. So really, there's essentially two, if you will, this is like the memory where our code lives, right? There's two things. There's instructions here, and there's instructions here. And when they get loaded, when they load here, it's actually load and decode, right? If that makes sense. So basically, code that we write that was compiled into instructions by the compiler is actually getting loaded into this I-cache and decoded into a series of microcode instructions, which are not necessarily a one-to-one correspondence with our instructions we see. So what I'm about to say next is true for microcode instructions, not instructions we see. And sometimes you will have the benefit of knowing what that microcode is, sometimes you won't. It depends on how documented the processor is that you're working with and how much the manufacturer wants to share with you and so on. Okay. So when we pull these things into this I-cache, what the I-cache is it's just like a cache for data like we were talking about before, but all it does is cache decoded instructions usually. And then the processor is reading out of this, right? It's fetching some instruction out of this, okay? So on one cycle, what is happening is it is going to go and fetch some number of instructions, right? So it's going to fetch. And maybe that number might be as many as, say, 4 instructions, right? Why did I don't know what just happened there. Stop drawing. It could be like 4 instructions. It could be who knows how many. It depends on the processor. It's going to fetch some instructions, okay? And it's going to fetch them potentially out of order, right? So depending on the processor, in the old days this was very simple. It always fetched them in order. Nowadays it doesn't even necessarily fetch them in order, right? So the processor is going to have a thing. It's going to look at some window of instructions in the microcode. It's going to fetch some instructions it thinks it can do, and it will issue, I think up to 4 is how many it typically issues on a modern processor, but I'm not going to say. It's going to issue some number of them, right? So it fetches some number of them that it thinks it can issue, right? And they go in here, right? So maybe I have instruction 1, this is instruction 0, instruction 1, instruction 2, instruction 3, right? So I fetch these instructions, and then I'm going to issue these instructions. So on this cycle, it will look at these instructions, right, and issue them. So they go off to parts of the chip. They're going off to parts of the CPU to be operated on, right? So these go out to some units. We don't know what kind of units they are inside the processor. Maybe one's an arithmetic logic unit, so it's going off to an ALU. One's a memory unit, it's going off to fetch some data. I don't know what. But point being, we're going into this instruction stream inside the iCache. We're getting back some things. We're going to issue them. Now, what happens in here? I said order question mark. What basically happens in here is modern processors, in order to speed things up, now issue things out of order. What that means is that if the instruction stream said A, B, C, D, E, F, G, these are some instructions that I want to do, there's actually a part of the processor that will look at these and go, oh, okay, I can execute A now, I can execute B now. C I couldn't execute because C actually depends on A and B to have completed, right? C uses like a result from B or something like this, right? And a result from A. It's like adding the result of A and B or something. So I can't issue that right now. But I could still issue another instruction because I could issue like 4 instructions this frame. So I'm going to grab D and E as well, even though C isn't there, because they don't have any dependencies on C, let's say. And it will bring all of those up and remember that it hasn't executed C, so that later when A and B complete, it can grab C and issue it, right? And so modern day Intel processors, for example, are heavily, heavily out of order. They work around the latency that you can imagine here, where if you have to, if I have to wait for these 2 things to be done, I can't issue this, right? They work around that by having a very large window of instructions they look at and grabbing maximally from that window, right? So hopefully that makes some sense. Okay, so once it gets those and it issues them, they go out into what's generally called a pipeline, right? And this is actually the first step of that pipeline, okay? And the pipeline is actually enumerated in cycles. So on a cycle, what's actually happening is this instruction issue is happening, but also simultaneously on that, these units are working on whatever the last instruction was that they were given. And each of those instructions may take a certain number of what's called pipeline stages to complete. So if I do an add here, an add, for example, might take 2 stages. So let's say this was an add. Here's the ALU unit, gets the assignment on the add. Maybe that takes 1 cycle, maybe on the issuing cycle, like it could be most of the time. I'd actually like to say that this is not really a line here. In fact, I probably shouldn't have drawn that line. Let me remove that. Typically, I believe, and again, I'm not a hardware guy, so don't take this with a grain of salt. But typically, on the cycle that it's issued, it does the first part of the work in the unit, right? So typically, this 1 cycle here, right? And so here's another cycle that's happening, and here's that pipeline, okay? And these are the stages. So this is stage 0, this is stage 1, etc. So let's say this is an add. This is going into what's called an arithmetic logic unit, an ALU, which is things that do things like adds, ands, ors, mass, bit operations, basically, right? It's going to go into a unit that's free, right? And it's going to do stage 1 of the add. So this is going to do add stage 1, okay? And then on the next processor cycle, it's going to move into the next stage of the add, which is going to do add stage 2. Okay? And then only on stage 3, let's say, does that actually complete and it gets written out, right? And so you typically have this concept, and I don't know, again, you have to look up in the documentation for any given processor, for any given operation, what this actually looks like for any given number of instructions, but that's what a cycle actually means. It's 1 tick of these stages, right? So if I say to you, how many cycles does an add take, and you tell me that it takes 2 cycles to complete, then what that means is it's going to use this stage, and only after that will the results actually be available, right? Okay, so hopefully that makes some sense. Everybody clear on that? Everybody clear on that? I don't even know. Are we clear on that? Who knows? I'm just going to assume you're clear on that. You can ask questions in the Q&A. All right. Why do they do this? What's the point of this pipelining? Well, the reason is because this way, It's a way of reusing parts of units at a faster rate, right? It's kind of the same reason that you have a washer and dryer separated when you're doing laundry, right? If you think about it, right? Let's say that I have, I'm just going to do it. Let's say you have a washer and a dryer in your house, right? Let's say you have a washer and a dryer for clothes. Okay, most houses in America have this. It's a common thing for people to have. Not so much in other places, like in Japan, a lot of people line dry things, which is in fact better for the environment. In America, yeah, people are like, environment be damned, we're gonna have a robot wash and dry our clothes. So anyway, let's say you have a washer and a dryer, right? Well, if you think about how that works, right? You typically have, here's my washer, here's my dryer, right? I put some clothes in, right? So clothes load 0 goes into the washer, right? And then on the next, you could actually think of these as the stages. So stage 0 is I load in the clothes to the washer, right? When the washer's done, we go to the next stage, right? Where 0, clothes load 0 goes from the washer to the dryer. And if I want to, I can now use the washer again. So I can load the washer with clothes load 1, right? While 0's in here. And then the next time around, 1 moves out, 0 goes to the laundry basket, right? And it's ready. It can go somewhere. It can be used, it can be worn, whatever. 1 moves into here, and 2 would load in, right? And what you can see, hopefully, by doing this, right, is if I was to do it this way, how many loads of laundry, right, can I actually do in a fixed amount of time? Let's take a look. Right? So 2 would move here, nothing would go in, 1 comes out to the laundry basket, and finally here, the last time, I'm going to take 2 out of the dryer and into the laundry basket, right? So how many do I need here? I've got stage 1, stage 2, stage 3, stage 4, stage 5, right? So you can see, essentially, when I did it this way, to do 3 loads of laundry, right, I only needed 5 operations through my washer and dryer, right? Now let's suppose I had some other mythical device, although they do have these, which is the washer plus dryer, which takes as long as a wash plus dry cycle. So it would take 2 stages, right? So if I do my wash plus dry, I load in 0, right? And it's still in there the next phase, right? And then finally here I would get it out, right? If that makes sense. In fact, I guess you'd look at it like this. Here I would get it out, right? So it goes in here, and it comes out. Next one goes in, comes out. Final one goes in, comes out, right? No pipelining. And what you can see is if I take the same amount of time, right? If this takes the combined time of both of these, then I actually blow a whole stage to do my 2 loads of laundry. I've wasted 1 whole stage because this is 6 stages and this was only 5 here, right? Because I can use that first stage, I can get that extra stage in there, right? And you know, if I keep going, right, it gets worse and worse for this mode, right? So if I'm in stage 5 here, let's say I go to stage 6, right? Here's my washer, dryer, right? Out comes 3. If I wanted to do it here, I would have to go to 8, right, to get 3 out. And so now we're a whole 2 faster. And what you'll basically see is as I crank the number up, it keeps taking 1 more to do this one than this one. So it just gets worse and worse and worse and worse and worse until basically asymptotically, it's always twice as long to do anything through this kind of a pipeline than it is to do it through this one. So basically processors, in order to maximize the value of all of the circuitry that they have, they now are all based on a pipelining model like this, right? They're all based on a pipelining model because by being based on a pipelining model, they can use the first part of something when the second part is completing, and it gives it a way to sort of reuse circuitry when there are dependencies, right? I'm going to zoom out a little bit here. Hopefully that makes some sense. Okay, so that gets us another part of our puzzle here, right? Which is in this thing. Actually, I guess I want to be in here right now. So we've got our code memory, we've got our iCache, which has our microcodes in it. We're grabbing things, we're issuing them, right? And what we have then is we have two pieces of information that we need to care about, right? We have a number called throughput, and we have a number called latency. And for every one of these instructions, we would like to know, if possible, what both of these things are going to be. Latency means how long does it take for an instruction to go from being instantiated, for being issued, sorry, to being complete, right? So that's end to end. And throughput is a number that tells me how many of them I can do if they're pipelined fully, right? So this is assuming issuing back to back, right? So translating that into our washer-dryer diagram, right? The latency does not change based on the pipelining, right? The latency, the amount of stages it takes for these to go, or cycles, right? The number of cycles it takes to do my wash and dry, right, is going to be 2 no matter which of these I do. It takes 2 cycles for me to wash and dry something. And so that is the latency number. If I have something that I need wash and dried right now, I have to wear it, I'm going to a meeting, it's the only thing I can wear, it's going to take me 2 cycles. So that's latency, okay? On the other hand, if all I care about is I have a ton of laundry to do, it's laundry day, I want to know roughly how long it's going to take me to do these 100 loads of laundry. Throughput is your number for that. That tells you how long it takes if you cut out the startup and shutdown time, right? This is typically called drain out, which is basically to flush the pipeline, right? I don't know if there's a term. I don't remember if there's a term for startup. It might just be startup, which is basically getting the pipeline going. So basically what throughput tells you is how long does it take for things to push through the pipeline once we've lopped off the drain out and the the startup. And it's basically saying if I put one in, how long does it take to get one out? I don't care which one, right? And in this case, that's 1 for here, and it's still 2 for here. So this is a latency 2 throughput 2 system, basically, and this is a latency 2 throughput 1 system, which means this is twice as fast as this guy for operating on large sets of data, but if you're just operating on one thing, they're the same. Okay? So basically what that tells you is if you only ever do 1 load of laundry at a time, you'd be way better off with a washer-dryer combo because you would have to do less work yourself. But if you wash lots of loads of laundry, you want a pipelined one that's a washer and a dryer, right? Okay. So typically when we're talking about performance, we're only ever going to talk about this throughput number because latency, and I shouldn't say that. With respect to instructions, we will use the term latency for other things. With respect to instructions, this we typically don't care about a whole heck of a lot because typically our goal is to structure the code so that we're always working on things in a pipelined fashion so that we're not waiting around for the latency. So when we look up things like how long it takes to do an ad, what we're going to be looking at is what the throughput is for an ad, not what the latency is for an ad, because we're going to assume that we're always operating on a lot of things at once. Now, sometimes that won't be true, but that's our goal anyway. Okay. So hopefully you understand that. That's pretty straightforward. And so let's talk about where latency does actually come into play. And this is, again, measuring essentially the same thing, but in a different context. Let's go up to our caches, right? So the place where latency really does cause us a huge problem, and it means latency and throughput translate exactly, basically, over here. Unfortunately, we care about them usually in the opposite way, but sometimes not. So we'll talk about this in a little more detail. What am I at here? Oh, man. We have gone through almost all the time. All right, so basically, this is going to be entirely a Blackboard session, basically. That's all right. This stuff has to be covered. Okay. So throughput and latency actually, typically throughput, for whatever reason, typically bandwidth is what's actually used to talk about memory. even though they kind of mean the same thing. They're not exactly the same, but you'll see in a second when I tell you what they are, whereas latency is exactly the same thing. Latency just means exactly the same thing and is used in both contexts. All right. So what happens with our memory, our cache, and that sort of stuff? Well, again, this diagram where we've got stages of a pipeline that are issuing, so we got instructions that issue, they retire, et cetera, right? This whole diagram is how we think about what the processor does with stuff that it has, right? That it has in its registers that it can operate on now. But the question is, what about stuff that the processor does not have, that it has to go and get, right? And typically we've got two things to worry about there. One is the total amount of memory that we can move through the processor at a maximum speed. And that, again, is like sort of the throughput. It's called bandwidth, typically. But that's like our throughput number. That means if everything's flowing smoothly in a perfectly pipelined fashion, how much memory could we just move in, right? There's like a bus. There's a thing called a bus. That takes memory off from the motherboard. It takes the contents of memory from the motherboard and drives it into the caches, right? That thing. And similarly, it's not really a bus, but there's lines that allow the cache to travel from the cache memory on the chip into the register store on the chip, the register file, right? And that also has a speed, a maximum thing. So there's a bandwidth on both of these, right? And the bandwidth is the total maximum amount of memory that you could move. Typically, you don't care that much about that for cache bandwidth, but sometimes you do. And you almost always care about that bandwidth for your memory, right? Because the maximum bandwidth to and from memory just determines the total number of stuff you could possibly ever operate on, right? It's the speed with which things can cycle through the processor, and whatever that speed is, that's the maximum you will ever be able to operate on stuff, right? Because at a bare minimum, even if you did nothing but move it from one place to another, it has to come into the processor and back out again, right? So the bandwidth to the memory, typically given in like gigabytes per second, for example, right? That memory bandwidth is what determines how much memory we'll be able to move through the processor at peak, okay? The latency on the memory, again, exactly analogous to what it was in the instruction case. The latency on the memory talks about how long it takes from the time we ask for a piece of memory to when we will get that piece of memory back. And it works exactly like instructions. If we issue a load, and let's say it takes 300 cycles to get memory, we will have to issue that load, and then 300 cycles will transpire before we get that particular piece of memory back, right? What that means is that if we were actually going to do that load, and the load could issue at speed, right? If we literally just issued a load, had to wait for it, and all of our instructions were operating on whatever that thing that was loaded was, like whatever it was getting loaded, we were going to operate on it right away. If that's how we were working, we would literally suffer a 300 cycle delay while all of these instructions wait for the result of this load to come back, right? Pretty horrible, because 300 cycles is a ton of cycles. Add, like I said, is like 2 cycle throughput, right? So it's just a massive hit. And that is not a made up number. Like memory often will be 200 cycles, 300 cycles to access. That's not unusual, right? It's certainly probably in the hundreds, even on very fast memory systems. So, or I guess it could be better if you have a very slow processor. In the old days when processors were extremely slow, memory was instantaneous. It was basically, it came right to you, right? But as processors get faster and faster, the memory can't. So that's what happens. The cycle count keeps going up. All right, so hopefully that makes some sense. And basically what that means is that is where this whole, there's this concept you've probably heard, right, of a cache miss. A cache miss is very expensive, you hear, right? What a cache miss is, right, is it's that the structure of this thing here, where we have these caches on the processor and then memory that fills the caches are what we load from and so on. Basically, these caches, like I said, like 16 cycles or something like that, might be, I don't know, that's like an L2 speed, I think, right? I don't know what an L1 is, maybe 2 cycles, I'm not sure. But point being, these caches are way, way faster to fetch from than memory. So if you can write algorithms that tend to work entirely out of things that are in the cache, and do not have to go to main memory, you will not suffer a cache miss. A cache miss is when you ask for something and it's not in the cache, so it has to go to main memory to get it, right? Your code will run much, 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 much faster because it will never have any of these latency hits, right? And what's important to understand here is the management of how this cache is filled is a huge part of modern optimization. Basically, there are instructions we can issue, we'll see them as we go, called prefetches. And what a prefetch is a way of telling the processor, hey, look, I need to tell you some stuff to put into the cache because I'm going to need it later, like 300 cycles later, and I want you to get it going now so that when I can do a bunch of other operations, and when I come back, the thing will be in the cache, right? So there's a tremendous amount of this sort of thinking about the cache, thinking about when to fill it, and how to do as much work with the stuff that's in the cache as you can before flushing it out again, right? Before it gets replaced by something else, in order to avoid these very, very expensive latency hits. And to that effect, this window here, this thing I was talking about with the out of order window, that is yet another way that the processor tries to overcome that latency. You can imagine some code that's not particularly good that does some loads like this and then starts doing adds on the loads, right? And that stuff's not, it's never been seen by the processor before, it's not in the cache, it has to go out to main memory, so it's got 300 cycles to work with. If this window is pretty large, if this window is like 50 or 100 cycles worth of stuff it could do, it can start grabbing things while it waits for that load and not waste all of the 300 cycles, right? Another thing you may have heard of is hyperthreading, right? You've probably heard of that, right? Well, what hyperthreading is just a processor keeping two states internally, right? So maybe I have state 0 and state 1. And it's exactly like it's like having two total processors. So all of the state of the processor is represented in both of these states, right? And all it does is it basically allows you to give it two sets of code to run as if you had two separate threads, two separate processors, right? But what it will do is whenever it sees that one of these would stall on a memory hit, right? If it's like, oh, I ran out of things in this window to execute. There's no more things for me to grab. I'm waiting, all of them are waiting on memory. It'll flop over to the other state and see if it can grab anything. That thing will then do some work and it'll probably end up stalling on some memory and it'll switch back to state 0, right? So hyperthreading is yet another way that Intel has tried to introduce technology basically to get around this fact that the memory is very, very slow, right? So there's basically lots of things in here that are designed to sort of hide that thing. These are called latency bubbles, right? Which are basically times when the processor is waiting on memory and literally can't do anything because everything it might want to do is waiting for a very long fetch to memory, right? Hyperthreading is one way it gets around that, right? And this memory window is the other one. And the rest of them, it relies on us to issue prefetches, to write cache, good thing that has cache coherent, it's called. So basically stuff that uses the cache efficiently. It's all up to us, right? All right. So now we come to finally, and I guess this is perfect, we're right up at the end here, we got about 8 minutes left. So now we come to the end of sort of the introduction to thinking about what's actually going on. And the next, I guess, so this will be good because tomorrow we can literally just talk about optimization, the process. So this is optimization, essentially the platform. So now you get like, this is what we're trying to think about, right? What we're trying to think about is we have a CPU and a GPU. Right now we're only concentrating on the CPU, but almost all of this stuff also applies to the GPU, oddly enough. But we're only thinking about the CPU right now. So we're thinking about the CPU. Our goal is to figure out a good set of instructions that does not have too big of a footprint, right? So it doesn't blow out this iCache, right? Because there's a cache where the instructions come from. So we're even thinking about not making our code too large, if that makes sense, right? We want a stream of instructions that's not too large, that does the right set of operations to maximize the amount of time it is operating on things in this cache, right? That knows what memory it's going to use ahead of time if possible and will pre-fill the cache with it where possible, right? That can be split up potentially among multiple hyperthreads and perhaps even multiple processors, let's say, to maximize the number of things that can be considered by the processor at any given time. And finally, whose instruction stream, as well as possible, issues the maximum number of cycles, issues the maximum number of instructions it could on every cycle, and in so doing is keeping this pipeline maximally filled with the things that we want it to do, right? If we can do that, we can get the most out of this 107 million cycles per frame that we have, and turn that into a very fast, high performance piece of code, right? And all of these things can come into play depending on the type of code. Some type of code, it's all about the memory. It's all about managing how the memory comes through. In other types of code, it can be all about the instructions. It's all about figuring out a good way to structure how we're doing things. But in most pieces of code, it's both. It's figuring out how to make sure the memory doesn't stall you out, and then once you have it so that the memory doesn't stall you out, it's about making sure that you do the least amount of work on it as possible, right? So that is optimization, okay? Now, I'm going to mention an adjunct here, and this is not something really that we'll talk about too much in this particular pass, because we're going to start at the base level of optimization, which is about how to just write the code so that it runs quickly. But there's another kind of concept here, and we might say that this is performance. And performance is the hardest one to think through because there's so much domain knowledge. Like you see all this stuff I had to draw out here, right? All of this domain knowledge. I didn't even talk about everything. I didn't talk about aliasing of the cache. I didn't talk about any of that stuff, right? So basically, like, performance is the one that has the most domain knowledge of the processor. Its adjunct is efficiency. And efficiency is the easiest to understand. It will literally take me less than the last couple of minutes we have here to tell you what it is. Efficiency means just not doing work you don't have to do, right? Efficiency is all about the algorithm, okay? So when we're talking about performance, we're usually talking about how to make a particular algorithm run as fast as possible using all of this nastiness and thinking through all of this complexity, right? Which you have to do if you want stuff to run quickly. If you want to be really good, you got to do it, right? But there's a whole other side to the coin which happens before you even really talk about this part, which is what are you actually doing and did you have to do it all? Because a very inefficient algorithm makes it so this performance optimization really isn't that interesting, because a more efficient algorithm that isn't performance optimized might actually beat it. Because let's say that I have some algorithm, whatever we want to do, right? In fact, we already saw this once, right? Do you remember when I first showed you how to fill the triangle, right? We had a triangle, and we just iterated over every pixel on the screen and said, is it inside the triangle, right? Because I was just trying to prove a point, right? I was just trying to say, here's how the algorithm works, right? That ran incredibly slowly. So slowly that just that one triangle, right, that was a little tiny triangle, would totally tank the frames per second. We then switched to only iterating over the things that were inside the rectangle bounding box of the triangle, and it got much faster, right? Sorry, it wasn't a triangle. I think it was actually maybe a rectangle. I don't know, but you get my point. That is an example of efficiency. We didn't do any performance optimization. The cost to compute any given pixel was exactly the same, right? But what we did is we checked less pixels, right? And so no amount of this kind of optimization is ever going to make up for efficiency. And so you always do want to make sure that you've done some work to make sure you're reasonably efficient before you start doing this. But in this case, we kind of know roughly what we're doing. We'll talk about a little bit of this because we do have a little bit of it to do in the software renderer, but most of our work on the software renderer will be this kind, because we kind of know at the end of the day that we gotta do pixel filling, right? Okay, so that's everything really about optimization in terms of the high-level overview. We have efficiency, we have performance. Efficiency means doing the least amount of work that you can do to get the result that you need. And performance is structuring the data and the actual operations on that data in such a way that they move through the processor in the least amount of cycles that they possibly can, right? And like I said, we probably won't hit the idealized performance for anything we do. We won't spend enough time on performance to get the absolute best. What we'll be shooting for is like the 80% case or whatever, like, you know, a pretty well optimized algorithm, but it could easily be beaten by somebody who wants to spend a month just working on this algorithm, right? Not algorithm, I should say, but basically the way of writing the algorithm, if that makes sense. So that's basically how to think about what we're trying to do. And so tomorrow what we'll do is we'll talk about what are the steps that we want to do that, like how do we actually do that? This is how much we have. How do we think through how we're going to work with those cycles and that sort of thing? How do we come up with an estimate for how many cycles we think we should be taking? How do we check against that? How do we measure how much we are taking? All that stuff, that's what we'll talk about tomorrow. For now, we will go to the Q&A since I introduced a lot of stuff on the stream. Just in case anyone has any questions, I'd like to just kind of have a brief Q&A where people can ask about them. So if you do have a question, please go ahead and ask it now. Put Q: in front of it, and I will see if I can clarify things for you. Atomic Lick, would you be willing to make more Blackboard episodes? This is very informative. I always make Blackboard episodes when they come up. If you have something in particular that you think we didn't cover in enough detail on a previous episode, please let me know and we could do a Blackboard session of it eventually. But anytime I come to a point in Handmade Hero where I need to explain something, we do a Blackboard episode. And we have had multiple Blackboard episodes in the past when we have gotten to those things. So I never skimp out on the Blackboard. When it's time to Blackboard, we Blackboard. Grumpy Giant 256, are you going to be using anything like VTune for measuring performance? I don't know, probably not. I think we'll just probably RDTSC it. But I don't know. I'll ask, because just correct me if I'm wrong, VTune still costs a lot of money, if I'm not mistaken, and I'd like to keep the stream to things that people can actually use themselves. So we'll try to just write enough of our own stuff that we can do it, and leave VTune as an exercise for the reader with $500, unless they're giving it away for free now. I'm not sure. How are instructions written in cache memory? I have absolutely no idea. To be honest, I really don't. I have no idea. That would be a great question for someone at Intel. I don't know if they document it. They might, but they might not. That may just be a trade secret. I have no idea. So, you know, I've programmed for 30 years now, and I've never once seen somebody talk about the actual format of the microcode, like literally the format. So I don't know. But yeah, I've never tried. Like I've never had a case. It wasn't like I tried to go find it and couldn't find it. I've just never seen it come up. It might be that if you do a search for like Intel microcode format or something, or x86 microcode, x64 microcode format, maybe there's a page somewhere that talks about it. Maybe Intel's got a doc on it. It could be in the system architecture manual. I don't know. But yeah, so I don't know. That'd be a great question for someone at Intel. Is it public? And if so, where is it? Do we manually issue prefetching, or is that something inferred by the CPU by looking at how we access memory? It can actually be both. But in our case, what I was talking about on this diagram is manual. Actually, when they introduced SIMD instructions into the processor way back in the Pentium days, I think it was the P6 maybe introduced them. I don't know. It might have been the P5 with MMX stuff. It's too long, I don't remember. But way back when, for forever ago, they introduced manual prefetching to the processor. So basically, if you write some code and you find that you're getting a lot of cache misses, but you know which memory you did need, and the processor is not predicting it properly, you just put in prefetches. If that's the only problem, you can just put in prefetches that say like, okay, when I'm doing this part of the loop, go prefetch the one that's like 4 iterations past here or something, and it goes each time, you know, so that it always leads it, you know, like a sniper or something, kind of leads it, and the processor will then always know, oh, okay, I got to bring that in, right? They also have non-temporal stores and stuff. There's actually quite a few, probably not as much. If you're a hardcore optimizer, I'm sure there's quite a few things that it doesn't do that you would like to be able to do with programming the cache. But there, you know, for a lightweight optimizer such as myself, there's actually plenty of instructions in there for stuff like prefetching and non-temporal stores and stuff like this that allow you to kind of, you know, if you're just having a basic problem with the cache, you can fix it. Stuff like cache aliasing and these sorts of things, which are things that I like only vaguely understand and have never optimized around. You know, they, a hardcore optimizer might be like, I wish they gave me more microcontrol. I could do more with it, whatever. And that's, to give you some perspective, that's why some people really loved optimizing for the things called the SPUs on the PlayStation 3 on the Cell processor. There was this thing called the SPUs, which were basically things whose cache was essentially fixed. It was like 256K of cache that you microprogrammed. Like you said what to move in and when to move out and when, and what to move out and when, and you just had complete control. And so the programmer could do whatever they wanted, and they were able, people who really like that fine-grained optimization, that's just a lot of power that they don't have with an Intel processor, right? I know this is a long way off, but after Handmade Hero is done, do you plan to continue educational streams? I can try to, yeah, but I probably at some point will want to stop doing them 5 days a week. So maybe we'll do like one educational stream a week after Handmade Hero is done or something like that, just to make it a little easier on me. How often do you estimate the actual amount of work prior to implementing a feature versus just implementing it and measuring it? So it depends on the thing. If I'm actually if I actually have some code that I want to be optimized, I always do at least 2 things. One is I try to figure out how, at peak speed, how fast it should go, right? And 2, I try to sort of figure out what my target speed would be for that, right? Like, I try to get those in mind. So I basically say, all right, let's say that everything issued exactly right, and I did the minimum number of ops for this math that I need to, and here's the processor I'm on, and I have this many cycles per frame. What speed should this thing run at, right? I almost always do that if I'm actually trying to optimize. That said, I am not a great optimizer. Like, I'm not the guy that you want to take advice from necessarily. So that may not be such a great idea. But I always like back of the envelope computations in that way. A back of the envelope computation is basically, which is what I'm going to talk about on next stream, basically is going, okay, just a rough estimate, how fast should this thing run? And the reason that I like that is because it gives me something to measure against. So I can go, if it doesn't turn out to be something within a reasonable percentage of that, I can say why. What's the thing, what was I not thinking about that's causing me to not get what I want, right? And so, like, for example, if you get into a situation where you're like, I should be able to do this many loads and this many multiplies and this many stores all pipelined properly, this should work out to this, and it's not, that's a great time to go call up Intel, call up whoever, and be like, ask your optimization friends, what's going on here? Can you give me some information? And I've seen great results from that. Some optimizers who are much more serious than I am, like Mike Sarton, for example, I've seen them do stuff where they end up at places where they're like, this is running too slowly, and I've computed everything out, and I know it is. And they've gone and talked to Intel, and they've gotten Intel to run like top secret traces of the code that they can't even see necessarily how they were doing them, because it's like on internal only stuff. And Intel will send them back, oh, the problem is that there's a thing in the processor that works like this, and you're hitting it because you're alternating these 2 things. And it was like, okay, right? And so a really, really hardcore optimization guy knows the boundary that's stated in the docs, sees if they can hit it, and when they don't hit it and don't know why, they ask the processor manufacturer and find out. And that's like the hardcore thing, right? So I always at least try to do the first part of that process, which is to let me know where I'm at relative to what I should be doing, because I think that's a pretty important thing to have, because otherwise you don't really know where you're at. You're like, I don't know, like, is this code optimized or isn't it? Who knows? Because I don't know how fast it should go. And if I don't know how fast it should go, I don't know whether how fast it's running right now is pretty fast or pretty slow, So. So if memory takes a few hundred cycles, if the instructions have to reach out to the hard drive, what impact would that have? The answer is a lot less now because of SSDs. So it's getting better. But the way to think about the hard drive is just as yet another piece, right? So I think we drew this diagram a long time ago in Handmade Hero, actually, but since it's a little more relevant now, I'm going to draw it again. You could think of it this way, right? Register, L1, L2, L3, memory. Just add another box. Drive, right? And you could even do two of them, drive and network, right? So cheapest, right? This is like almost free. This is very expensive. And everything in between. And that's why you end up with this sort of concept that latency, you know, somewhere around here, latency starts being this kind of dominating thing that you're thinking about. Because it starts getting so big, you know, 300 cycles up to, you know, thousands of cycles or tens of thousands of cycles, or way worse depending on what we're talking about fetching from here. What you end up doing is somewhere, you know, as latency starts to dominate as you move in this direction, that's why everything tends to be overlapped when you get out here in a huge way. Like drive stuff you issue, you know, like on the thing that I'm doing at work right now, I issue drive reads 2 seconds in advance of where they would be used or more, right? So we're talking 6 billion instructions in advance. I'm issuing them at least, right? And sometimes more, depending on the circumstance, right? So that's just how that is. Starchy pancakes. 2 questions. Are there ever any cases where we have to worry about one of our instructions being decoded into multiple microcode instructions without our knowledge? 2, in optimizing, have you set up the code in such a way that you can optimize things function by function with this eventuality in mind, or will we have to restructure some of the functions to allow them to be optimized? So question 1, the answer is typically I never think about microcode all that much. Because the throughput and latency numbers tend to be all you really need to know for baseline optimization like we're doing. If you're trying to do super hardcore optimization, then yes, actually that is something you need to worry about because of this part that I was talking about back a little earlier. You can sort of see exactly why this comes into play. This thing with the issuing, it's the issuing that kills you, right? So when things get decoded into multiple microcode instructions, what that means is it puts more pressure on your issuing count, right? If something gets blown out into 7 micro instructions, that means that that thing you thought was 1 instruction actually is going to take 2 cycles even just to issue everything of. If they're not independent, possibly more. It could take up to the 7 instructions if they're all serially dependent, right? And so having something broken out into microcode, if they're serially dependent and there isn't code around it that can be executed to hide that bubble, could absolutely be a problem. But again, is that common? No, that's not the common case. The common case is you don't have to think about microcode. Will it happen if you're a super hard code optimizer? I suspect the answer is absolutely yes. Will it happen if you're just a reasonable optimizer, such as myself? No. You don't tend to push things to the limit of peak performance where you're going to have to start thinking about things like that. Question 2, whether I've set up the code in such a way that we can optimize things function by function. The answer is generally yes. And generally that's a good thing to be doing just in general. Like when I try to write code, I try to write code knowing what things are expensive. And really what that boils down to is order stuff, right? Remember order notation? That's the thing that's like ON squared, right? That sort of thing. Basically what you want to think about is how many iterations, right? That's really like what you want to think about. So you got for loops. Sometimes you got for loops inside for loops and so on. That little piece of code in the middle, how many iterations does it have to do, right? And if you think about that in the back of your head, you're always going to kind of know what your slow parts of the game are going to be a lot of times, right? Because the things that execute the most frequently are the things that have that happen. And so in the case of the software renderer, pixels, right, is a loop over x and y, right? So it's ON squared in the size of the thing on the screen, right? It's filling in an area. So I just tend to know when I'm writing a software renderer, okay, what are the things that are going to happen in the software renderer? I know that I've got relatively big sprites on the screen that fill up a fair number of pixels. I know that I have a fairly low number of them by comparison, right? So like I've got the number of sprites, maybe that's 10,000 or something total. I know I've got the number of pixels, I know that's like, millions, right? And I can just tell, like, this is the thing that I need to be the most concerned about, and this is less so, right? And so you're already, when you're thinking about writing the code, it should be obvious to you, just as you're typing it in, oh, what are the places here that are going to have to be optimized? It's that rectangle fill, right? That's going to be the very most important thing to optimize, and everything else is going to be secondary to that. So you got to make sure the code is all about allowing me to optimize that rectangle fill, right? Et cetera, et cetera. But at the end of the day, as long as you're not doing totally crazy stuff with your code, and this is one of the reasons why, again, I also hate object-oriented programming, is because typically I find that if you write stuff in a straightforward C programming style, just the way you would normally write the code tends to end up looking like how it will end up being when it's optimized. And the only time that doesn't happen is because of the fact that C's structs weren't designed when SIMD was a thing. And so typically you have to do a little bit of reorganization for the SIMD aspect of things. So that changes things a little. But I find that typically the way people normally write things in an OOP style is very different from how you would write them if you were trying to optimize things. And so that's yet another reason I don't like that paradigm. It doesn't mean you can't, right? It doesn't mean you can't learn to program your OOP in a style that makes it okay for optimization. It just means your natural instincts will often be wrong in that domain. And so that's another reason I like the C style, because I feel like people's natural way they might write something in C tends to be pretty close to how it should be laid out when you actually need to optimize it. Would it be inefficient to offload the cache to an SSD over or with minimal RAM usage, or with a late... Sorry, I'm not sure I totally understand the question. Would it be inefficient to offload the cache to an SSD over or with minimal RAM usage, or would the latency be too much? I'm not sure I understand the question. An SSD is basically just very slow RAM, right? So it sits at, again, the place that I drew, it sits over here in the hierarchy, right? And so you would never offload things to an SSD. You would offload them to memory first and then to the SSD, usually. Because you want to overlap that, right? You want to overlap that flush. But yeah, I'm not sure I totally understand the question, so sorry about that. Premature optimization is the root of all evil. What's your take on that quote? My take on that quote is it's largely a meaningless quote, unfortunately, because premature is the problem, right? It's obviously true, just at the face of it. I mean, well, I don't know if it's true at the face of it, because I don't know, the root of all evil might be a bit much, right? It might be that it's a statement that would be unequivocally true would be premature optimization is evil, or is bad, right? But the problem with that statement is saying premature optimization doesn't really help anyone, because how do you know what's premature, right? On the one hand, optimizing a bunch of things at an instruction level when your game is already running at 30 frames a second or something like that might obviously be stupid and premature. And yeah, that was a huge waste of everyone's time and makes the code more brittle, and because you can't change it as easily and whatever, right? So obviously that's true, but that's not normally what the thing that might make a mistake. The thing where you tend to make the mistake is, okay, do I need to store these things in a spatial hierarchy or not, right? Or do I need to do this or not, right? And the problem is doing those things or not doing those things tends to have architectural implications for the rest of the code, and it's not as simple as just not doing it until you absolutely have to, because doing it later might have to change how a bunch of stuff was architected, and then that optimization was too late. So post-mature optimization then becomes a problem. And so I find the problem with that quote is not that there's anything wrong with the quote itself, it's just that knowing whether something's premature or not is actually very difficult and is not as easy as the quote might make it sound. Is there any way to use or avoid hyperthreading to your advantage? Yes, and we will be doing that on the stream. We will be using both hyperthreading and regular threading in the renderer, and we'll talk about how to use those on the next stream probably. What do you tell someone who doesn't like Emacs? I tell them not to use Emacs. I just use Emacs because that's the editor that I'm most comfortable with, but I think everyone should use, provided they can be like roughly as fast as they see me code on stream. If you can code that fast in whatever editor you want, I think you're good. If you can't, then you might want to consider either learning how to use your editor better or switching to another editor, not necessarily Emacs, but just another editor that's better, so that you can be at least roughly as fast as I am. Because that's the speed that I think you want to roughly go at. If you're going significantly slower than I'm going, that's probably a bad sign, especially because I'm coding slower on stream than I tend to code in real life because I'm talking and stuff. So if you can't at least hit that speed, I think you want to think about whether you're facile enough with the editor that you're using. But it doesn't have to be Emacs. Does hyperthreading reduce maximum bandwidth because it has to switch between states, or can both states operate at the same time? Typically, yeah, the bandwidth is typically shared between hyperthreads. So yeah, the bandwidth doesn't get any higher just because there's hyperthreading. Saying reduced bandwidth is a little bit hard to say because bandwidth is a measure of how much stuff is moving into the processor. So that obviously is always the same. But if you have two hyperthreads, they are sharing that bandwidth, obviously. So you don't get double the bandwidth just because they're the two hyperthreads. Let's see. In your experience, what drives the good enough optimization, and how did the novice guys get a handle on that? Actually, it's very simple. The good enough part is actually pretty straightforward. You have a game. It needs to run at 30 frames a second. You have some expensive stuff you're doing in that game. It is good enough when it runs at 30 frames a second on your target platform. That is the end of it, right? And so it's usually actually pretty easy to know when you've hit that. Now, hitting it can be hard if you're trying to do too much. But, knowing when you've hit it is easy. The game runs at 30 frames a second. Done, right? And so for any given piece, how you know how close that piece is to being optimal is by doing that back of the envelope calculation that I was talking about before. It's basically about having some idea of how fast the processor could ideally do this workload, and then seeing how fast you are doing that workload, and that's a good measure of how optimized your performance is. Efficiency, there's not a lot you can do about efficiency, I'll be honest with you. Efficiency is very hard to know. Because how do you know if the algorithm you're using is very efficient? Sometimes you can figure it out by going, oh, well, I know that somebody has proven this algorithm takes at least this many iterations, right? It's ON provably, and I'm only doing ON, so I know I'm relatively efficient. Sometimes that's true. But sometimes the thing that you're doing, it's very hard to know because it's like, okay, well, yeah, it's proven to be ON, but I'm accelerating it with this lookup structure that makes it a little closer to ON most of the time if it's distributed well, but what if it's not distributed well? Maybe I could use a different spatial partition, and then it would be distributed better, so blah, 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 blah. And like, there's all these things where it's like really kind of nuanced. And so that part is actually very hard to know. And sometimes the answer is just you iterate on both the algorithm and the performance because you just don't know until you can get yourself down to 30 frames a second. That's just, and it's a grind, and there's nothing else you can do, right? And that's just sometimes that's the case, right? So it looks like that's about it. We're out of time, and I don't see any more questions on optimization, really. Pseudonym73, you were posting a GitHub link there for latency numbers. Do you want to go ahead and post that to the forum so we can like have it up there? I could tag it as like a permanent post or something. That might be cool. But for now, let's go ahead and wrap things up. Tomorrow, hopefully, now that we've kind of gotten all the preliminaries out of the way, I can just talk briefly about some of the stuff that we need to do so we can actually get to some code, because I'd like to do a couple code things relatively soon for us to start working with. But anyway, yeah, there we go. That was basically a giant Blackboard session on optimization topics. Hopefully that set the stage so that when I when I go through talking about this optimization, I reference things. I'm hopefully that will be nice and easy for everyone to understand, so that when I reference something like an L3 cache or the latency of this instruction or the throughput or whatever, we'll kind of all be on that same page. So if some of this was confusing, please go back and rewatch this or ask questions on the forums, so that we can kind of all be on that page, because as I go through this, I'm going to just refer to those things like instruction, throughput, and that sort of stuff. I'm going to refer to those and assume that we now are clear on what those mean. All right. Thank you, everyone, for joining me for another episode of Handmade Hero. It's been a pleasure talking about optimization with you. No coding today. Hopefully tomorrow. It's been a pleasure talking about optimization with you. I hope that cleared some things up and got us on a good, sort of on the same page for what we're about to do for this week, next week, and so on. If you would like to follow along with the code we're going to do this week, and you want to pre-order the game, that gets you the source code. So if you go to handmadehero.org, you can pre-order the game here, and it comes with the source code. So you can download it every night after we're done here. The forums are a great place to go if you have questions that you want to ask, or you want to look up some stuff that we've got up there, like ports to Mac or Linux, and also we've got some coding resources, annotated episode guide, just stuff, good stuff up there. Check that site out if you're trying to learn from the stream. We also have a Patreon if you want to support the video series and what we're doing here. We would love that. You can always subscribe there. Very much appreciated. And we have a tweet bot which tweets the schedule. So if you're just trying to catch the stream live on any particular day, that's the place to go. It'll always tell you the schedule. Today we're 5 p.m. Pacific Standard Time every day except Friday, where we're doing a morning stream at 9 a.m. So please check that out, just so you can check that schedule out so you can remind yourself what the schedule is. It's a great way to do that. So thanks everyone for joining me, and I will see you guys tomorrow. Take it easy, everyone.